let's go to the next problem. I'm doing 3 problems for this particular video, so let's go to the last one. Here's the problem. 1982 study of 18-year-olds to 24-year-old men and women in the United States. They were asked the question, have you been on at least one bad date in the last year? Now, a bad date was clearly defined for them. Whatever they might have thought as a bad date is irrelevant. The results showed that 37% had been on at least one bad date during the past year. A 2018 survey of 1,641 randomly selected 18-year-olds to 24-year-old men and women were asked the same question, and 645 responded that they had been on a bad date during the past year. Testa claimed that the 2018 study showed that the proportion of bad dates among 18-year-old to 24-year-old men and women is different from the 1982 results. So let's just deconstruct all this real quickly. And we have x equals 645, n equals 1641, p hat equals x over n, ends up being this number. Q hat equals 1 minus p hat. P is what we assume to be truth unless this little study shows otherwise. Q is equal to 1 minus P. Level of confidence, well, there's none given. So what do we assume it to be? It's 0.95 as our default level of confidence. Alpha equals 1 minus the level of confidence, which is 0.05. And alpha over 2 is 0.025. So to test the proportion, the correct sampling distribution is the standard normal. This is a two-tailed test because of the key phrase, is different from. The irony is that if it said, is it the same as, it would also be a two-tailed test. Two-tailed tests are when you're testing to see if two things are equal or the same, or if you're testing to see if that they're different or not the same. The critical value for this, we have to use alpha over 2 because it's a two-tailed test and we're splitting up alpha into two tails. The way to do that is the norm.s.inv of 0.025, which means I have two critical values. On the left side, it's the negative, or negative 1.96. On the right side, it's positive, or positive 1.96. The null and alternate hypotheses are, my null hypothesis is P equals what we commonly accept as truth, unless this study tells us otherwise, and that is from the study that was conducted in 1982, 37% or 0.37. My alternate hypothesis, because this is a two-tailed test, we have P is simply not equal to that, or P is not equal to 0.37. Of course, we have to calculate the test statistic, and the formula is the same as it always was, and that comes out to be, my test statistic is positive 1.93. Now, 1.93 ends up being not inside of either rejection region. It's just slightly outside of the rejection region on the right-hand side, right over here. What do we do in a case like that? Because none of the previous problems had that. In a case like that, when the test statistic does not fall within the rejection region, we fail to reject the null hypothesis. In other words, we cannot reject things are not the same as they always were. We can't reject that the population proportion of those are basically the same as it was in 1982. And that's what this part says right here. Because we fail to reject the null hypothesis, in layperson's terminology, we can simply restate the words in the problem. With a 95% level of confidence, it seems that the proportion of bad dates among 18 to 24-year-old men and women is not different from the 1982 results. And again, that's because we cannot reject, or we fail to reject, that they are equal. Let's put all of this on a spreadsheet. Here we are in spreadsheet mode, kind of a hybrid mode this time. We have x equals 645. We have n equals 1641. Automatically calculates a p hat and a q hat for me. P, that's what we accept as truth, remember, and that's from the old study, the 1982 study, which says that 37% had been on a bad date within the past year. So we'll say 0.37. Q is automatically calculated for us. My level of confidence for this one, remember, there was none shown, so that's 0.95. My alpha is 0.05. Alpha over 2 is 0.025. Well, critical value left tail doesn't matter. Right tail doesn't matter. This is a two-tail test. My critical value ends up being negative 1.96 and also positive 1.96. And we saw that on the diagram. We'll quickly go back to that in just a minute. And my test statistic automatically populated to be 1.93 positive. So let's go and see what the diagram looks like again. The critical value on both sides, negative 1.96, positive 1.96. My test statistic ended up being about 1.93, which down here, this is where it's shown. It does not fall in my rejection region, so again, I fail to reject the null hypothesis. Since I fail to reject the null hypothesis, we can say that things are not different from the 1982 results, or things are the same as the 1982 results. Well, we're done talking about hypothesis testing, about a population proportion. Have a great day.